Okay, now that you know the basic definitions of the hyperbolic, sine, hyperbolic, cosine, some of the graphs, we shall now move straight into the derivatives, okay? And it turns out that really the derivatives and the integrals of these hyperbolic functions gives us a very useful integration result, okay? And this integration result, we sometimes see it in a lot of problems, okay? And to solve it, we really need to know the hyperbolic derivatives and hyperbolic results, okay? So we just move swiftly along to the first derivative of Ching x. Let's just do Ching x first, okay? It will just simply be cos x, okay? Yeah, this is just a simple derivative. And then if we were to differentiate, okay, cos x with respect to x, we will simply get back Ching x. Okay, and the last one is that if we differentiate hyperbolic tangent, I'm not too sure what is the nickname for it, okay? If you want, you can just let me know. We differentiate hyperbolic tangent with respect to x, we get hyperbolic secant square x. The only difference is that for the trigonometry, there's a minus sign. If I'm not wrong, so right now there's no minus sign. Okay, these are the three basic results, okay? But we can also write it in the chain rule format, okay, if you are interested, or if you need to write it in chain rule format, I should say. Okay, Ching x, sorry, so I will differentiate with respect to x, but I'm going to put Ching u, so it's expressed in another variable u. I will just simply get cos u du dx, okay? Simple chain rule implementation, okay? I bet all of you know that. Okay, so I will just simply show the first one. And the proof is very easy. It's very easy to derive because all we have to do is we just convert the hyperbolic function into the number e format, okay? And then we can just differentiate accordingly. So differentiates Ching x, okay, is equals to differentiate. Now what's the definition of Ching x? Is simply half ex take away e minus x, right? So I'm going to differentiate this with respect to x, I'll get half, okay? Differentiate ex, I will get ex. Differentiate e minus x, I get the same thing, but I need to differentiate the power and multiply it, so I'll get a plus. Minus 1 multiplied by minus is e minus x, and this gives us cos x, okay? Very simple differentiation, okay? Quite easy, you might think. Okay, so from here, we will just, and knowing the other result, okay, we can just simply write the reverse, okay? You write the integral. So if we integrate Ching x with respect to x, we will get cos x plus c, right? If we integrate cos x with respect to x, we will get Ching x plus c, okay? And then finally, if we integrate tangent, hyperbolic tangent x, okay, with respect to x, we will re-express it as the top would be Ching x, the bottom would be cos x dx, okay? And knowing that when we differentiate cos x, okay, we get Ching x, so we can just simply see that this is a standard form and write ln, okay, cos x, okay? Because ln, this one will go at the bottom, and then we need to differentiate this one and put it at the top, which is Ching x plus c, okay? So a very basic result for the hyperbolic functions. Now here is where we will derive a very useful integration result, which needs a bit of algebra and differentiation, but I hope that you can bear with me, okay? And it comes from the first derivative of Ching x, okay? Now here is how we will go about doing it. Okay, I'm first going to express it as an inverse, okay? So y, okay, now recall the graph, okay? Recall the graph here like that, okay? The graph is like this, right? So basically, I would say we are able to take an inverse, or at least implement an inverse function, okay? Because I'm not too sure what the ruling is, but we can implement the inverse function, okay? So I need to check on that, okay? So now we'll just write as y is equals to inverse Ching, okay? Okay, I hope you got me on that one, so you follow me on this one. So I will just now write, okay, because later, what I'm going to do is I'm going to differentiate y. So I want to find the first derivative of y, but first, let's just see whether I can re-express this equation over here, okay, and somehow eliminate the Ching function, or the inverse Ching function, okay. So I'll write sine y is equals to x over here like that, okay. So however, what is sine y? Sine y from the definition is half ey take away e minus y. equals to x. Doing some rearranging, I will get ey take away e minus y equals to 2x. Okay, and then now I will multiply by ey. Okay, ey, because I want to eliminate this minus y over here. So I'll multiply by ey, I get e2y. Bring this over to the other side, minus 2x ey. Then I will minus 1. Okay, I hope you can see that, right? Okay, so now what I can do is that I can now solve this equation, because if you were to notice, this equation is written in a quadratic form, right? Okay, where ey is taken to be the s. Okay, the x, sorry, ey, there's an x here, there's an x squared here because it's e to the power of 2y. Okay, then I will just immediately write it out as this. Ey is gonna be equal to 2x plus minus square root of 4x squared plus 4 divided by 2, okay, and then we can just immediately write that as x plus square root x squared plus 1, okay. Basically, we are eliminating the negative square root, okay, because we can't get a negative value for ey over here. It doesn't make sense. If we take away the negative square root, there's a chance that we might get a negative value, okay, but ey, as you know, can't have a negative value, okay. So basically, now taking the logarithm, so I will take ln on both sides, I will get y is equals to ln x plus square root x squared plus 1, okay. So this is basically just re-expressing the inverse sine function over here. Sorry, inverse Ching function over here, okay? This is just re-expressing the inverse Ching function over here. However, this is not entirely what we want, right? Remember, we want the first derivative of the inverse Ching function. So, if I dy dx this one, okay, it will be equivalent to dy dx this one over here, which is differentiating this one over here, which if I were to look at it, I believe is fair, it still can be done, okay? Maybe we'll try both sides and we see whether we get the same results. That's option number 1. Option number 2 is that I can use implicit differentiation to differentiate this one over here, which is the, I would say it's a easier and more algebraically neater method, okay? But let's just do the both, okay, out of interest, okay, and exploration. So how does that work? Well, I just simply would write Ching y over here, okay, x, just bring the Ching function to the other side, as in, you know, I multiply, or I apply the Ching function, then I can implicit differentiation, okay. How do I do that? Differentiate both sides with respect to x. This one is a 1 over here. This one will be cos y. Now I need to differentiate the inside with respect to x, right? But what is differentiate y with respect to x? Is simply dy dx. Okay? Then dy dx, I will bring the cos y over the other side, and now I can write 1, take away, using the identity, okay, 1 take away this identity here, cos y squared take away Ching y squared equals to 1. Okay, so now I got the cos y at the bottom, okay, so this would be 1 square root, so I'll put a square root here, okay, 1 plus Ching squared y, okay. However, what is Ching squared y? Ching squared y is x squared, right? So it's equals to 1 divided by square root of 1 plus x squared. Okay, a lovely function like that over there. Okay, now finally, I'm just erase this graph over here. Okay, you can do the other one. You know how when I express y as the logarithm function, I believe if you just differentiate it, you will get the same result. You can go ahead and try it. Okay, so now what do we get from here? Well, I'll just simply put the dx over there because I can separate the variables. Okay, put the dx over there, so I get 1 plus x squared dx, and now I will integrate both sides with respect to the proper term, okay, the proper differential dx and dx dy term. So I will integrate, okay, 1 over square root 1 plus x squared with respect to x is gonna be equals to integrate of 1 of dy, right? Okay, I hope that's easier to understand. So this would just simply be y, and y would just simply, so integrate 1 with respect to y will give me y, but y is Ching, inverse Ching x. So what I get is that this result is equals to inverse Ching x, okay, plus c, okay, and that is what we got over here. Is that correct? Yeah. This is the result that we have, which I will just write in more clearly over here, integrates 1 over square root 1 plus x squared dx is equals to inverse Ching x plus c. Okay? And this is highly useful because if you were to study mathematics or calculus, this form comes up very often. Okay? Now, you might be thinking that, I'm not going to say a function like that, but if you want to train yourself to solve the higher level undergraduate problems, such as the William Laurel Putman, I'm sure that some of these integration results may come in, okay? And this is why you need the hyperbolic sign, okay? So, a good result to know, it's also a good result to know, that you integrate 1 divided by square root of 1 plus x squared dx, you will get a hyperbolic function, Ching x plus constant c, okay? Lastly, using all this, let's solve the problem of the catenary. Let's go.